Hi, I'm Meike Hettwer, and I'm presenting our work on system-level cortical maturation and how it links to adolescent resilience to adverse life events. Adolescent development is marked by heterogeneous levels of plasticity across the cortex, and especially higher-order cognitive networks remain pretty malleable into early adulthood. At the same time, we naturally all live in an environment that influences developmental processes. So if we face adversity, it can have detrimental effects on both development and mental health. Yet many of us experience more or less nice situations throughout our lives, but most maintain good mental health. And this is a concept called resilience, or positive adaptation to adversity. Here we were interested in how change in resilience capacities throughout adolescence is linked to plastic changes in brain maturation, with a special focus on myelination because it's plastic in itself, but at the same time also functions to attenuate plasticity. We use data from the Neuroscience and Psychiatry Network, which is an accelerated longitudinal cohort. So individuals entered the study at different ages and were then followed up for 1 to 2 years. And based on this sample, we computed a stress resilience score. We identified a latent factor from several mental health questionnaires, and this factor reflects general distress or well-being. In a separate subsample, we then predicted general distress from available adversity measures, including adverse life events, childhood trauma, different kinds of family settings, and then conceptualizing resilience as a better than predicted outcome based on adversity levels, we extracted residuals from the model as resilience scores. We linked individual differences in resilience to microstructural brain maturation in 2 overarching approaches, making use of the accelerated longitudinal design of the data. In the first chapter, we studied longitudinal change in myelination using magnetic transfer, or MT, as an imaging proxy for gray matter myelin content. And here we studied how the rate of change in this myelin proxy is linked to intra-individual change in adolescent ability to cope with stressors. In a second chapter, we made use of the whole age range, so 14 to 26, which required a cross-sectional design in that we investigated whether especially adaptive and especially susceptible individuals differ in how regional microstructural maturation is embedded and synchronized with the rest of the cortex. So looking at intra-individual maturation first, we observed a higher rate of change in our myelin proxy in adolescents who become more adaptive in primarily the left prefrontal cortex. And these effects generally followed a posterior to anterior axis of MT development, so the imaging correlates of behavioral change and adaptivity are found at the anterior, but not the posterior end of this developmental axis. Having identified the relevance of prefrontal structural maturation for resilience, we then next also aim to see whether prefrontal functional maturation plays a role too. So we again looked at longitudinal change in functional connectivity in a seed-based fashion, and we defined the prefrontal cluster we just identified as a seed. We observed more maintained functional integration within primarily the default mode and frontoparietal network in individuals who develop towards higher adaptivity, whereas we see a segregation in individuals who become more susceptible. At this point, we've seen that adolescents who show a positive change in their ability to cope with adversity show a higher rate of prefrontal myelin-sensitive MT change, which follows a general organizational axis of MT change and links to maintained levels of prefrontal functional embedding. Now, while the last chapter looked at intra-individual change between 2 measurement time points of the same individual, we now also made use of the whole age range of the sample, so 14 to 26, and looked at maturation from a global, more system-level perspective. We used regional profiles of our myelin marker, so we sampled the MT contrast at 10 cortical depths and computed microstructural profile covariance, MPC, so the similarity between these profiles across regions. And the underlying assumption of this approach is that regions that mature to become more similar are also likely developing to become more integrated with each other. For the system-level perspective, we computed a maturational index which captures how age-related change in microstructural profile covariance is related to MPC baseline patterns. To do that, we applied a mixed effects GLM of age to each edge of each node and extracted an MPC pattern at age 14 as baseline, as well as age-related change. Now, positive correlations between the two variables reflect that regions that were structurally similar at baseline also become more integrated. And this is what is called conservative development, as you basically strengthen what you already have. But a negative correlation between the two reflect reorganization. So regions that were similar at baseline become more differentiated. And this is termed disruptive development, but it's not pathologically connotated. It's just part of adolescent brain development and reorganization. Note that this disruptive development can mainly be observed in a frontoparietal heteromodal midline. For a better understanding of how this midline reorganizes, we generated a previously described principal axis of age-related change in MPC. And this axis captures maximally different maturational patterns in two so-called anchors, one being more idiotypic or sensory-motor, and the other one more paralimbic or ventral. And it's assumed that a heteromodal midline differentiates throughout adolescence to become either more sensory-like or more paralimbic-like. So regions in this midline do not only change most in their cortex-wide embedding, but this change also seems to be least synchronized with the two main anchors of the age-related change axis. Now, knowing that microstructural maturational trajectories vary quite a bit across the cortex, where do we see links to individual differences in stress resilience? Group differences in the maturational index reflecting change as a function of baseline patterns, so reorganization, were very subtle. Those regional effects we do see indicate more conservative or less disruptive development in adaptive adolescents, meaning their change pattern is more closely coupled to baseline patterns that are already established early during adolescence. We also observed a general expansion of the MPC developmental axis, reflecting a clearer differentiation of the two anchors in more adaptive individuals. And at the same time, we see a clearer bimodal distribution of loadings on this axis. And this is to a certain degree failed to establish in more susceptible adolescents, meaning that this heteromodal midline is less synchronized with anchor profiles, which define the MPC axis of age-related change. So in susceptible individuals, there is more room for diverging development in this heteromodal midline. Together, both main angles of our analyses underline a certain benefit of stability in microstructural differentiation, either achieved through faster myelination or through differentiation following paths that are already set up during early adolescence more closely. The first chapter of our analyses underlined a central role of dynamic intra-individual change in prefrontal structure and function for adolescent resilience. And alterations to the prefrontal cortex and insula have previously been observed following early life adversity. But here we underline that this may indeed be related to adaptation to exposure rather than exposure per se. This also raises the question of directionality here. It is possible that adaptive or even accelerated prefrontal maturation facilitates the maturation of top-down cognitive and affective control, and therefore argues for an inherent link between cognitive resources and resilience capacities. And that is a mechanism that could then also be targeted in interventions. However, already at the physiological level, we also know that the PFC is among those regions metabolically affected by hormonal stress responses. So it's also for us an open question if a certain resistance to alterations induced by, for example, stress hormones is a protective factor in itself, or a consequence of protective environmental factors that we have not yet investigated. From a more system levels perspective, we observed slightly more differentiated and in a few parts more conservative development in a group of comparatively more adaptive individuals. Generally, we assume that there are less extrinsic and intrinsic constraints on the differentiation of this midline, which may also allow for more individual differences in developmental trajectories. But our findings point towards a slight benefit of a less is more strategy, where development of this midline is more closely drawn towards predefined anchors and more closely coupled to patterns already set up during early adolescence. Or put differently, in the current sample, higher susceptibility to adversity was linked to stronger deviations from baseline patterns. Thank you for your attention. Special thanks to my supervisors, Sophie Falk and Simon Eickhoff, and please feel free to reach out at OHBM.